Welcome back to Let's Code. Today we have something that's a little bit, I'm going to say it's exciting. So I have some issues with this shader that I've been working on, and you might notice that my monitor looks a little bit different than it usually does. On the left here, we've got Windows Terminal, and on the right here, we've got a Visual Studio Code running on my Windows device. And that is because today we are going to be working with RenderDoc, or more accurately, I'm going to show you how to get a program that you've run with Bevy into RenderDoc to debug shaders and GPU programs. This isn't going to be a full RenderDoc tutorial, so don't worry about that. It's just going to be me setting up the program that I'm working on right now, and then showing you a little bit of the RenderDoc API, or the RenderDoc UI. So in this case, you can download RenderDoc from the drop-down here. It only really runs on Windows, although there is also a Linux build. This is why we're on the Windows PC today, because this doesn't run on Mac OS. So I'm going to pull up RenderDoc, and RenderDoc is going to open here. I don't know if I can actually make this any bigger for you, so we're just going to have to live with the fact that the UI is, maybe not the greatest UI. But for what this program lacks in UI and sort of modern sensibilities, or the ability to zoom the UI so I can show it on this video, it makes up for in the absolute amount of just insight that it gives you into your shaders and your GPU running programs. So in this case, I've got Bevy examples, Compute 3D. That's the program that we're running today. Let's do a cargo run so you can see it. These builds take a little longer on my Windows PC than they do on my Mac. I'm not sure if that's my fault or not. So this is the program. Basically what we have here is a 3D texture being generated by a compute shader. We're not actually going to look at the compute shader today. We're just going to look at the vertex and fragment shaders. But the compute shader builds a 3D texture. That 3D texture is basically just a bunch of simplex noise in a bunch of layers. So it's 720 by 720 by 720 for this 3D texture. And then right now I'm just painting that onto the cube in different ways by sampling that texture. If we look at the code, we can see there's a bunch here. The vertex shader is not very interesting. It's basically the default vertex shader. And then I also have this view position here. So it's the inverse view. So the camera view, basically, matrix multiplied by the world position of the vertice that we're looking at. So that gives us the view space coordinates of these vertices. I need the view space coordinates of these vertices because what I'm trying to do is ray march a vector through this cube into that 3D texture. So you can see I have a bunch of code here to do that, but it's not quite working correctly. So that's why we have RenderDoc. Now, it's often quite hard to figure out kind of what the types of things are. You can see I've got WGSL analyzer here giving me a couple of the types. So for this lower bound, it's going to be a vec3 of f32s, which we already knew because we built a vec3 right here. But really I need to figure out how to set this lower bound and this upper bound. And what I'm really interested in right now is this view projection that we were just talking about. Because what this arraybox DST function is doing is trying to find the edges of this box that are close to the camera and far from the camera. So basically we're shooting a ray into this box. We need to find when it collides with the front face and when it collides with the back face. Or it may not collide with the back face, or if we're in the box or something like that. I'll go over all of the ray marching stuff after I get this shader working. Right now we're just going to go into RenderDoc because you can see it's rendering right here. The code for that is just sampling from the fog texture with a sampler at some XYZ coordinate and then returning that color. So this is the 3D texture as we would see it if it was mapped to all of the individual sides of the cube. But my problem is that I have no idea how far away from the camera this is. I have no idea what those view projection values are. So this view position here, I don't know what this value is. I have no idea what numbers go in there. I have no idea what kind of space that I'm looking for here. So what we're going to do is we're going to open RenderDoc, and I do a cargo build here. And then this would be a copy from the target directory. In this case, it's target debug compute 3D because that's our Bevy program, right? And then I go into RenderDoc, and in here there is a executable path. So I'll open this up. Now, after I built it in Target and copied it over, there's a Compute 3D right next to our assets folder. That's super important because this Compute 3D, or this our bevy game basically is going to look for this assets folder to be next to it. So that's why I've copied this binary over from the debug folder instead of trying to run it in a different spot. So I'm going to select the binary, the executable, and then it's going to set the path and the working directory. We can also set command line arguments and environment variables, but we don't need to in this case. There's also a bunch of other checkboxes and stuff that I haven't actually looked into at all. But now we can go down to this launch button and launch our bevy game. And our bevy game will start to run kind of inside of RenderDoc. So in this case, what I'm going to do is press F12, and you'll see the top left, this stuff went away and came back, and we captured frame 388. So that's all well and good. Let's stop the program from running, and it'll load in this capture for us. So I'll make this as big as I can, but I can't make any of these elements bigger. So sorry if you're on a phone. Basically on the left here, we've got frame 388. We've got the start of the capture. We've got a number of things that happen in here. In this case, you can see it copying a buffer, copying a buffer, copying a buffer, copying a buffer. This one right here is the time. So we're extracting the time from our bevy app, writing that into a buffer, and then sending that to the GPU. This is that copy instruction. And the time uniform buffer here is actually a string that we set in our Rust application. So if I go into time here, time.rs, which is where that code happens to be, we create this buffer inside of this GPU time plugin that I've created. And in the buffer descriptor, we set this label that just says time uniform buffer. That is the exact string that's showing up over here on the left. And now we've got basically one frame of our game entirely from start to finish. And we've got all of the instructions and all of the buffer copies and all of the draw calls and all of those kinds of things. So there are two passes that are interesting here. There's the main opaque pass 3D, which does a couple things. And then there's the main transparent pass 3D, which is where I'm actually attaching to call this draw indexed, basically. So one of the interesting things we can do here is if I go to the texture viewer and I right click here, you can see on the right hand side that it's picked a pixel inside of this cube. So it'll tell me which pixel I clicked. In this case, it's 652 by 395, and the color is about half. So 0.5, 0.5, 0.5, 1. It gives me the size of the color attachment texture, so 1280 by 720. It gives me the sort of data format. In this case, it's the BGRA sRGB. And if I go to history here, it'll show me the history of this particular pixel, which in this case is not very interesting because there's only one draw call. But if there were multiple fragments that overlaid on top to figure out whatever this is, we would see all of those on the right here. Now for me, what I think is really interesting is we can see not only this texture and the color at this draw call, or when this draw call is happening, we can also see the pipeline state. So in this case, we've got some vertices, we've got our Vertex Shader here, VS, got a couple of other things in here that aren't, I think, used in this pass. We've got the rasterization step that tells us what we're sampling and how we're sampling it. We can see the cull mode, we can see the viewport, which is really interesting. And then we get to our fragment shader and we can see the bindings and the actual data, so the actual texture that is represented by our 3D image and the sampler itself. So you can see this is a 720 by 720 by 720 texture, and it's a 3D image. And we've got this sampler as well. Then we've got the frame buffer here as well. Not something I'm going to dive into right now. Basically, all I want to say is that there's, like, for any draw call, for anything that's happening on the left-hand side here, all of the stuff that happens for the GPU, you can click on one of these and you can find out what the state of any given thing is. Now, in this case, one of the really interesting pieces is the mesh viewer. And this is actually where we're going to find our explanation for what is actually going on. In this case, we can see VS in, so Vertex Shader in, and it's this box here with this triangle, and we're working on this vertice in the bottom left of this square here. And if we look at the VS out, we can see that that is in fact the bottom left, because when we were actually running our program, our camera was looking at this at a specific angle when we captured the frame. So this is how our cube is getting drawn onto the screen. These are the triangles it's using. This is the vertice that we're focused on right now. We can see this vertice right here in this table up top. Maybe I can make this a little bit bigger. And there's some stuff we can do here. We can do like solid color shading or secondary, which is the UV map colors here, which is really cool. There's a whole lot more you can do here, such as showing previous instances and stuff like that. All I need to see is the data in the VS input up here and the VS output. So the VS input gives us the position of every vertex. So this is vertex index 0, 1, 2, 3, etc. And if I scroll to the left, we can see the position, the normals, the UV coordinates here. And if we look at the output, we can see the clip position, the point size, the world position, the world normal, the UV, the vertex position, and the view position, which is the thing that we're looking for. So again, I just want to point out that we've defined some data. So there's this vertex into the vertex shader and this vertex output, which is the data that we're sending out of the vertex shader. If we look at the vertex output, we can see all of the things that we're seeing inside of the debugger. So here's the clip position, and then a bunch of stuff for the mesh vertex output that we pull in from Bevy, the vertex position, and the view position. The vertex and the view position are custom things that we decided to put here. So that's just totally our decision. I said, hey, in location 5, we're going to put a vertex position. In 6, we're going to put the view position. And what RenderDoc allows us to do is just take a look at what these values are when they're getting passed out of the vertex shader, which is incredibly cool and is very, very entertaining. So if I look at the view position here, I can see that the kind of XYZ is somewhere between -7-ish and 7. I think actually the lowest value I see here is -64993. The highest value I see is 64993. The Y values are somewhere between -0.7 and 7.7, positive and negative. And then the Z position, or in this case, because it's the view position, this is the distance from the camera. This is going to be -5.5 to 6.7, -6.7, something like that. So now I have more of an understanding about what that view position is. When I go here and I'm looking at this inverse view, right? And I multiply that by the world position. Now, because of RenderDoc and because it's showing me this output, I know what kind of positions I'm seeing. I know that the distance from the camera is a negative number in this case. So if I wanted that to be a positive number, maybe something that I would do is change this to be view.view instead of view.inverse view. And of course, if we launch the application again, don't save the capture, and we captured frame 135 this time, and I'll close it and we'll load the capture in, and I'll go down to the transparent 3D pass and go to the draw index command. And then we pop over to the mesh viewer and just take a look at the values again. You can see that the view position here is now positive in the Z index, and the numbers have changed a little bit. So this is a representation of using different matrices to multiply against the vector that represents the position of the vertex so that we can get a position that is relative to the camera, to the viewer, basically, which is what we need to do ray marching into this cube. So yeah, that's that. And it is pretty easy to set up a Bevy app to be thrown into this RenderDoc application. It is free. I believe it's open source. It's MIT licensed. It's a standalone application, so you do have to download it and you do have to have either Windows or Linux to run it, but it can get you quite a bit of information about your shaders and how they're running and what kind of output they're giving and things like that. And if you want to go into it, you can bring up the actual textures that are being pulled in. We can look at the different slices. So in this case, it's a 3D texture. In this case, there are 719 slices, or 720. I think there's a 0 as well, right? So if I wanted to look at what it looked like at slice 574, I could see that right here inside of RenderDoc without having to do any fancy kind of like trying to render it out to the cube as slice 574 or something like that. And this is, of course, simplex noise. So it's if we go from like 271 to 272, it doesn't change very much. But if we start to make larger jumps, we can start to see a little bit more difference between them. And of course, this is a single octave of simplex noise, so it doesn't look that noisy, in my opinion. But in the end version of this, I'll probably combine quite a few octaves of noise to actually get the cloud generation to happen. But yeah, so this is a super exciting new frontier for me. This is the kind of the first time that I've opened RenderDoc and used it to actually debug something in my application. And now I know a little bit more about this view position that I'm generating from the Vertex shader, and given relative to the actual cube, what these numbers are going to look like so that I can develop a mental model of some of these values and some of these matrices so that I can figure out how to actually use them. So that's it. Just an introduction to RenderDoc today. I assume that as I use this more, I'll make more videos on it. But if you have any questions, I'm happy to answer them, happy to dig in, happy to share that on video. And I hope you have a great day, and I'll see you in the next one.